What if a chessboard could think for itself? A board that not only connects players around the world, but learns the way that you play and shows you moves you've never considered. All built at home and powered by a Raspberry Pi Pico microcontroller and my laptop. For this project, my aim was to harness the helpful features of digital chess and bring it to life on a physical, real-world board. I started by designing and 3D printing a piece that will serve as a spacer between the addressable RGB LEDs and a sheet of translucent acrylic. This piece also houses a Hall effect sensor that will detect a chess piece with a magnet embedded in its base. 64 of these pieces provide the structure for the chessboard. The walls of the pieces create a barrier between each cell of the board so that they can be lit up with unique colors without mixing. The 3D printing process made it easy for me to create a modular structure that housed everything. I had to solder wires to the sensors and glue them on the inside of the 3D printed board pieces. Next, I cut up a string of addressable LEDs and soldered them back together with wires between to get the spacing right, ensuring they would light up in the center of each square. The LEDs were placed on a couple of layers of foam board, and the square 3D printed pieces were put together on top with the wire leads from the sensors pushed through to the back of the board. The output circuit is easy. Addressable LEDs contain a tiny microprocessor that takes the information it needs to control the intensity of the red, green, and blue pixels and sends the rest of the signal down the line to the next LED. This way the LEDs can all be wired in series. A single output pin on the Pi Pico controls all 64 LEDs. Reading the input from the Hall effect sensors that track the chess pieces is not so easy. Each sensor needs to be paired with 2 additional components to function properly. A capacitor between the power and ground pins keeps the input voltage more consistent. A resistor between the power and signal pins pulls the signal high when there is no magnetic field present. When a chess piece is placed over the sensor, the magnet in its base pulls the signal low. The software keeps track of which piece is where, so as long as pieces are moved one at a time, this is all that will be needed to keep track of the state of the board. Not only did I need to add 64 resistors and 64 capacitors to the board, but I needed to collect 64 different signals with the microcontroller. A Pi Pico doesn't have that many input pins, so I needed to use multiplexers. Multiplexers are used to cycle between many inputs and send them in turn down a single input wire. The microcontroller can then cycle between several multiplexers to receive all 64 signals on the same pin. To organize all the circuitry on the back of the board, I cut up some perf board to use for the additional components. Each of these boards handles the circuitry for 4 sensors, so each row on the chessboard needs 2, making 16 in total. The multiplexers I have can handle 16 inputs, so I used 4 of these to channel the signals from 4 boards each. I used an additional piece of perf board to junction all the controller lines for the multiplexers and connected them to the controller. This project required so much soldering. I had to make around 1,700 connections to put this thing together. But now I have a robust one-of-a-kind I/O device that I can use for endless software projects. Besides all of the chess potential this thing has, it's basically an 8x8 low-resolution display. I can use it for pixel art, animations, and other smart games played within an 8x8 grid, like Checkers, Othello, or Connect 4. Building this chessboard was a fun challenge and a chance to bring new life to an old game. I hope it will connect players, help them learn, improve, and make every match a little more exciting. I'll also be able to play online or against a computer when I can't get anyone at home to play chess with me. Thanks for watching. If you're interested in learning more or doing a project like this of your own, you can find links to my project repository on GitHub and the parts I used in this video's description.